Hey everybody! Have you ever wondered what the major component that makes up the human body is? Water! Yes, it's water. It's all around us, and sometimes when you least expect it, you can make it do some pretty amazing things. For example, did you know you can take water that's flowing down and actually make it shoot straight up into the air? How, you ask? Well, it all comes down to the science of fluid dynamics. Fluid dynamics is the study of how fluids, like water, air, and even gases, move and flow. Sounds complicated, but stick with me and it will make sense. Alright, so even though we live in a world governed by physical laws, sometimes we need to pretend certain things aren't happening to make things easier to explain. Take friction, for example. In some cases, we imagine there's no friction at all, so we can focus on the important parts of the problem. Same goes for fluids. Fluids are dynamic, meaning there's a lot of going on inside them all the time. To keep it simple, we're going to make a few assumptions. For our examples, we're going to pretend the fluids we're working with are incompressible, meaning their density always stays the same. We'll also assume that the fluids flow smoothly with no viscosity. Viscosity, you've probably heard of it. It's how thick the fluid is. Water has low viscosity because it flows pretty easily. Honey, on the other hand, has a high viscosity and it flows much slower. But to keep things simple today, we're going to ignore viscosity because it adds extra complication. Now, imagine you've got some water flowing through a pipe and the pipe is narrow in some places and wider in others. What happens when the water moves through the narrow part of the pipe? Well, the key point here is that the mass of water moving through any section of the pipe is always the same, no matter where you are in the pipe. This is known as the mass flow rate. It's the amount of mass moving through the pipe in a given time, and it's the same everywhere in the pipe. Now, think of it like this. If you have 1 kilogram of water passing through a section of the pipe every second, the same amount of water has to flow through every other part of the pipe. This is called the equation of continuity. So, let's say you're an engineer working with a water system in a hypothetical city, and you need to calculate the mass flow rates of the water in a particular pipe. What do you need? Well, if you know the velocity of the water and the area of the pipe, you can use a little bit of algebra to figure it out. First, let's look at the cross-section of the pipe. The mass of water passing through a certain point in the pipe is the density of the fluid times the volume. Now, the volume of the fluid moving past this point is the area of the pipe at that section times the distance of the fluid moves. And of course, the distance a fluid moves per second is its velocity. So, putting all these pieces together, we get a new version of the equation of continuity. It tells us that velocity of the fluid times the area of the pipe will always be the same throughout the pipe. What does this mean in simple terms? Well, if the pipe gets narrower, the fluid has to move faster to give the same amount of mass flowing through the pipe. But wait, there's a twist. A fluid that's moving faster has less pressure on the walls of the pipe than a slower moving fluid. This brings us to Bernoulli's principle. It states that where the fluid is moving faster, the pressure is lower. Where the fluid moves slower, the pressure is higher. And why is this important? Because Bernoulli's principle helps us understand how fluids behave in different conditions. Now, Bernoulli came up with something called Bernoulli's equation. It looks complex at first, but it's actually a simple way to combine the energy forms in a fluid. Pressure kinetic energy, and potential energy. Bernoulli's equation is based on the idea that energy in a fluid stays constant. As the fluid moves, its energy doesn't change. It just transforms between pressure, speed, and height. Well, let's break down Bernoulli's equation. First, there's the pressure of the fluid times the volume, which is a form of energy. Then, the kinetic energy, the energy due to the fluid speed, and finally, the potential energy, because the fluid has height and gravity pulls on it. By dividing these energies by the volume of the fluid, Bernoulli's equation gives us the pressure, kinetic energy, and the potential energy densities all in one equation. And here's a special case, Torricelli's theorem. This uses the conservation of energy to calculate the velocity of fluid flowing from a small spot in a container. And here's a special case, Torricelli's theorem. This uses the conservation of energy to calculate the velocity of fluid flowing from a small spout in a container. According to Torricelli's theorem, the velocity of the water coming out of the spout is same as the velocity of a droplet that falls from the surface of the fluid. Imagine you've got a rain barrel and you're watering your garden from a spout. You want to know how fast the water comes out, right? So, using Torricelli's theorem, you can figure out that the velocity of water flowing out is the same as the speed a droplet would gain from falling from the height of the barrel. Want to try something fun? If you point the spout of your rain barrel straight up, the water will shoot up exactly to the height of the water in the barrel before falling back down. So today, you learned all about fluids in motion, the continuity equation, Bernoulli's principle, and Torricelli's theorem. Thanks for watching, and don't forget to check out more cool science lessons. See you in the next videos.